our topic 1 through 4 discussion, I'll be focusing on my team member Sierra Schlechel's problems here at the Fun Time Water Park. Here, topics 1 and 3 are covered, which are Bernoulli and hydrostatics. Here we have a water gun, which uses a Venturi meter with an attached manometer. We are applying Bernoulli at points 1 and 2, and we would like to measure the height difference. We are given the volumetric flow rate through the system. We are given the diameter at the beginning of the Venturi meter and the diameter at the end. Here, our knowns are stated, and we are finding the height. Assuming steady state, incompressible liquid, adiabatic, irrotational fluid, no change in gravity, no work, and no friction, and given the properties of the specific gravity of mercury, the density of water, we are able to solve this problem. First of all, we are able to apply the Bernoulli equation at points 1 and 2, as shown above. We are able to cancel out Z1 and Z2 as they are equivalent. As you can see, there is no height differences at point 1 and 2. In addition, we are able to cancel out the H of the pump, the H of the turbine, and head loss, as there is no pump or turbine present in the system, and we are assuming no head losses due to being no friction. We were able to here solve for the pressure difference. In order to do this, we needed to use continuity in order to solve for the velocity at point 2. Finally, we were able to use the hydrostatics equation in order to set equal P1 plus the density of water times gravity times height is equal to P2 plus the density of mercury times gravity times height. Solving for H, we were able to determine that the height difference is 0.104 meters. In order to account for extended Bernoulli, Sierra did another problem in conjunction with topic 6. Here she used the assumptions and did not cancel out the friction term. Here she needed to use head loss equations in order to determine the H of the pump. Continuing with our discussion of topic 2, we can see that there is a lily pad at a water park. The top of the pad is at the surface of the water with a rope holding it to the bottom of the pool. Assuming that the volume of the lily pad is 0.17 meters cubed with a weight of 150 kilograms, which does not include the weight of the air, we want to find the tension force holding the lily pad to the bottom of the pool. Here are our knowns. We are finding the tension, and we are assuming the water is incompressible, no entering or exiting fluid. Here we are able to do a force balance, which can be seen in this image above. We can see that you have the buoyant force acting upwards and the weight force and the tension force acting downwards. Now, assuming these forces equal 0, because there is no movement of the lily pad, we are able to plug in and solve for the tension force, which is then equivalent to the buoyant force minus the weight force. Now, we are given that the buoyancy equation is equal to rho Vg. Plugging this in, we can then determine that the tension force is equal to the buoyant force minus mg, which is equivalent to the weight force, and minus the density of air, volume, times gravity. This is crucial because the lily pad is full of air. This must be taken into consideration. Plugging in our known numbers, we are then able to determine that the tension force is equivalent to 194.16 newtons. Last but not least, we will be discussing topic 4. Here we have a water fountain. We are given that the ball weighs 600 pounds, it is made out of granite with a diameter of 24 inches. We are given that the water leaves from a source below with an opening of 1 foot and goes horizontal right after hitting the sphere, as shown here. With our knowns discussed above, we are finding our velocity at point 2. We are assuming that water is incompressible and steady state, and given the density of water and using momentum balances, we are able to solve this equation. Now, here we can see the momentum balance. We are able to cancel out the convective forces out because there is no m out. We are also able to cancel out the momentum with respect to time because it is steady state. Here, using the force balance on the sphere, we are able to simplify and have the force by water, which is equal to m dot v, minus mg, which is equivalent to the weight of the sphere, is equal to 0. Here we know m dot is equal to rho va, which we are able then to substitute here. Due to continuity, the mass flow rate is the same at point 1 and point 2. And because the momentum balance is done at the point where the water hits the sphere, we are able to include v2. Having this and subtracting the weight force, we are then able to solve for the velocity that is keeping the ball suspended in air. Here we are able to determine that the velocity is 17.4 feet per second. This shows that the water is at this velocity in order to hold up the sphere.